We're going to work through some additional examples of creating sinusoids and then making FIR filters that manipulate the corresponding output. Alright, so let's start with 3 sinusoids. Let's make one of them 500 Hertz, the other one 1000 Hertz, the other one 2500 Hertz. We're going to make a sampling rate of 10,000 samples per second. That should be fast enough because the highest frequency is 2500 Hertz. 2500 times 2 is 5000. You know, we're sampling twice as high as we need to sample. Okay, and it says that I want to make this 3 seconds worth of signal. So I start at n equals 0 and I end at 3 times fs. Alright, so we talked about this before. I just put some random amplitudes in here so that you could see the difference whenever we do the plot spec. You know, y1 is not as strong as y2 and y3 is stronger than both of them. Okay, so you put in the frequency term, then you do the point-by-point multiplication. Actually, that's not point-by-point, that's 500, the decimal point goes with the 500. So 500 point times n. These are all scalars, so this would actually work either way. Okay. And, you know, basically we've formed 3 sinusoids of identical length, which lets us in MATLAB add those together. All right. So from there you can listen to that. When you listen to it, here we go. Not very pleasant, but that's what it sounds like. Okay, we can also look at the spectrogram. I'm sorry, plot spec. Remember with plot spec, we're looking at sort of an aggregate of all frequencies. So we'll evaluate that, and you see this is the time domain signal. It's wiggling so fast you can't see it. It just looks like one solid blob. Okay, and then we see frequency components if we zoomed in on just the positive frequencies. We would see a weaker signal of 500, somewhat stronger signal at 1000, and the strongest signal at 2500 Hertz. Alright, so if you think about this, these really technically should be infinitely high, but this is a numerical approximation. We have a lot of data to work with, so this amplitude does get pretty high, but it's not infinitely high. And these ratios are not exactly right, but it's pretty close to, you know, this one being twice as tall as this one, and this one being 2/3 as tall, or this one being 2/3 as tall as the 6. Alright, but you see relative amplitudes are captured with this plot spec command. Alright, so let's get rid of that. From here, I wanted to make a filter. Alright, and we talked about in class how to design an FIR filter. So I want to keep only the 1000 Hertz term, so I need to get rid of the 500 Hertz term and the 2500 Hertz term. So I make a vector, alright, 7500 up to 1250, and then I normalized by the sampling rate over 2. And so because this is a vector, MATLAB properly interprets this as saying, oh, we must want a band pass filter. And in class we talked about A is equal to 1. And this lets us actually look at the freq command, lets us look at the frequency plot for this filter. So let's run that. Oh, the parameters are, you put in B, then A, and then how many samples of your plot that you want. Okay, so I put 1000, so we'll get a nice plot. All right, and so this is this doesn't look right, so let me rerun that and make sure it ran correctly. Okay, now it looks right. Okay, so this is a bandpass filter. I can make this a little bigger. Down here you see start to cut on around 500 and cut off. So when we get to 750, it's within the pass band of the filter. And so we talked about in class, you can't have perfectly sharp edges. So the order of the filter matters. If I reran this with 200, an order of 200 instead of 100, we get a little sharper filter, so you'd have to save both those plots, but you could play around with that and look at the sharpness of the filter. Alright, so bandpass filter. Alright, from there I want to apply that bandpass filter to the signal Y. So we do filter B comma A Y. So we put in the filter coefficients and we get the output in Y filter. So I can plot that and listen to it. So when I listen to it, instead of hearing this mishmash of 3 tones, you should hear just a single tone. Okay. Let's see. Oh, this ran this whole section, and at the end here, it pulled up a spectrogram. I was a little confused on why I was seeing a spectrogram instead of plot spec. So let me bring this down, and we can talk about it. All right, the plot spec, you want to look at the whole time, and there's only the 1,000 hertz signal showing up. Notice there's nothing showing up here. It's as if that had been completely removed. But you look over here in the plot spec, there's still some artifacts of 500. You see this green stripe here. Green's not as bright as red, but there's also a green stripe at 2500. Green's not as bright as red. So there's still some energy compared to these areas out here where there's nothing. There's still some energy at 2500 and 500. All right, so part of the reason for that is we normally would plot the spectrogram or plot things about the spectrum on a dB scale instead of a linear scale. So you can also do plot spec, I think it's underscore dB, little d, capital B, of Y filter, and still 1 over Fs. So let's run just that part. And when you look at this, what you see is something harder to interpret because the dB scale kind of makes things a little harder to look at. But you see there's a spike here at 1,000, I'm sorry, minus 1,000 and 1,000. That's our, sinusoid that we're keeping. And then over here at 500, there's a spike, and it's quite a few dB down, about, 80 dB down. So this really filtered that out quite a bit. Same thing over here at 2500. There's a little bit of 2500 still showing through, but it's mostly knocked out by the low pass filter. Okay, so I wanted you to be aware of things on a dB scale instead of a linear scale. Okay. All right, we could do the same thing and repeat this process and keep only the 500 hertz term. And in that case, a low pass filter would do that. So maybe you'd want to go a little past 500 to make sure we keep it. So maybe out to 600, and then apply the filter and the plot dB, plot spec dB, and take a look. Let me run. Oh, there we go. Okay, so from there, The strong signals now are the 500 hertz terms. 1000 gets attenuated, 2500 gets attenuated. Okay, so this is an example of how we apply MATLAB to generate sinusoids and then do practical filtering.